it's a great pleasure to introduce our next speaker, Manuel Eberl from Innsbruck in Austria, who's going to talk to us about computing Bernoulli numbers. And I think we were just beginning to see them beginning to compute there, maybe. Yeah. Anyway, so thank you.
Okay, hello everyone. So I'm a postdoc at the University of Innsbruck. You can see a bit of the university in the background, especially the mountains, most important part. So this is joint work with Peter Lammich, who's now at the University of Twente. But before I start with this, so someone, I think it was Alex Bess yesterday, told me that I should actually remind people what Isabel is, and I first thought he intended it as an insult, but I think he then clarified that it wasn't intended as such, but he was being serious. So let's do just that. So for everyone who's not familiar with Isabel, so Isabel is an interactive theorem prover, so very much like Lean or Coq, or some of you might still remember Mizar as well. The basic idea is, of course, to do mathematics in such a way that everything that you do gets broken down into the most basic logical inferences, like introduction of universal quantifier, elimination of universal quantifier, etc. And these are the primitives that the Isabel kernel understands. So everything you do is, in the end, gets fed through this kernel. And it's a bit different to Lean, as I understand it. I'm not an expert in any of this, but as I understand it, so Lean basically always records the whole proof. Whereas in Isabel, we, from the very beginning, one of the selling points was that we basically immediately forget the proof. It's basically more like the proof is streamed through the kernel, and once the kernel accepts a step, we just forget about it. And that, of course, has some performance benefits. And there's Isabel, and then there's Isabel Hall, and these things get conflated quite a bit these days, and the reason is, so Isabel was actually introduced as a generic theorem prover, where you can do all kinds of logic in, but it turned out that people mostly started to use higher order logic because it turned out to be presumably the most usable one, and it's definitely the one with the biggest library these days. So there are still some people working in Isabel ZF, but most people are using Isabel Hall these days. So these are often just used synonymously, though they're not. And so Isabel Hall has a fairly simple logic. It's more similar to systems like Hall Light or Hall 4. So it doesn't have dependent types. Turns out that you can actually get quite far even without dependent types. So you occasionally run into situations where you wished you had dependent types, but then from what I hear from Coq and Lean users, they occasionally run into situations where they wish they didn't have dependent types. So everything's a trade-off, right? And I would say Isabel's big focus is that we have very good automation and we have fairly high performance, and it was also I think it was one of the first systems to have proper parallelism. So we can basically process a single Isabel file, so we call these theories. We can process these in parallel quite well. So we have very fine-grained parallelism, and of course also more coarser-grained parallelism. So it all scales quite well to machines with lots of cores. And also very importantly, here we have a very large library. So not just mathematics, we also have a huge library of computer science, which I'm not mentioning here so much because I think this place is more focused on mathematics. So we have a lot of mathematics. I don't know how exactly it compares to Lean. I mean, Lean's library definitely grows much faster than Isabel's, but there is a lot of stuff there. And one thing where I think we're still a little bit ahead is complex analysis. So John Harrison made quite a bit of a huge development in Hall Light about complex analysis, and Larry Paulson ported over a big chunk of that, or probably all of that. And then Wendell Lee extended it quite a bit more in Isabel Hall. So we have now a fairly big development of complex analysis, which I use quite extensively, so that's also why I'm mentioning it. Not in this particular work that I'm going to present today, but otherwise I use that a lot. And also another big thing is this archive of formal proofs. So this is basically, it works a bit like a journal, but you don't submit papers there, but you submit your Isabel developments there. So it's more like a scientific data repository than an actual journal. And the entries are reviewed, but it's not like an extremely thorough review where we say, oh, this is not relevant or whatever. It's more like we just look at, does it make sense? Does it as far as we can tell, does it do what they claim they do? It does, and then we typically accept it, so we're not extremely strict there. And the important thing about the archive of formal proofs is that there is kind of this guarantee that whenever something changes in Isabel and it breaks an entry in the archive of formal proofs, the person who broke it has to fix it. So basically, as some of you might know, if any kind of piece of program code or also proofs, formal proofs tend to be very brittle with respect to change. So if you don't maintain these, then over the years they will just break completely. And then after, like, I don't know, maybe 5 or 10 years, it might be easier to redo it from scratch rather than fix all the problems that are introduced by the changes. So the archive of formal proofs exists to basically combat that. And so once it's there, we guarantee that it will run as long as Isabel exists, basically. And these numbers, I update these every year. So the last time I gave this talk was, well, a talk like this was in Bonn about a year ago. And there, I think the number was something like 740 entries, and now it's 820. So I did the maths. It's about, I think there's a growth of about 80 articles a year. And about, I forget the numbers. Yeah, okay. I think it's about 5 million lines of codes, and I think we get like an extra 500,000 lines of code every year. So it is quite a steady growth. And as I said, it's not just mathematics, it's also a lot of things about logic and a lot of things about computer science. So things like program logics, that sort of thing, and or like infrastructure to verify code, like C code, for example. And so the history is that, yeah, it was started by Larry Paulson a long time ago, almost 40 years. And nowadays, the core developer is Makarios Wenzel in Augsburg. So he takes care of a lot of the like just the basic infrastructure that the system actually still runs, and it runs fast. It becomes faster and faster. And Fabian Huch from Munich is also helping him quite a bit these days. And then there's like a lot of other contributors who just improve the library. Occasionally also maybe integrate some new automation tools, but mostly these days, not that many people actually do stuff on the core of Isabel that's relatively stable. The core library is also relatively stable. There's like minor additions here and then, but most of the big changes happen to the AFP or, well, to the more fringe parts of the core library. Yeah. And also a big change was that Makarios Wenzel introduced structured proofs in 2005. So before that we had these backwards apply style proofs with tactics. And since then we've moved very heavily to structured proofs, and you will see what I mean by that in a bit. And these are, Isabel is not the first system to have these, so Misar also had these quite heavily, and Isabel was, the structure proofs in Isabel were very heavily inspired by the Misar proofs. And I think that's definitely extremely useful because it makes the proofs more readable. So I'm still hesitant to call them readable because if you don't know Isabel and you look at them, they still look like a bunch of nonsense, of course, but there is structure there, and if you have a bit of experience, you can read these. And it's, especially if you want to port Isabel to other systems, so some of you might have done this already, it's definitely much easier, in my opinion, to port stuff from Isabel to Lean than the other way around, simply because the structure isn't there as such. And then there's the archive of formal proofs, so that was established in 2004. And okay, so now I'm just going to move on to some overview of random facts that we have, and there's a heavy bias here to things that I either did myself or I was somehow involved with, or that I just think are really neat. So it's definitely not a comprehensive selection of things we have, and I'm sure that there's many impressive things that we have that I omitted here. So one thing I did ages ago, and this is not a very big thing, it's just a kind of nice, neat little proof, which is just that an n-dimensional ball has a volume that is, well, this expression here. We have the prime number theorem. So the first version of this was done by Jeremy. I don't know when, it's like 2005 or something, I think. And that was the elementary proof. And then John Harrison did the analytic number theory proof in Hall Light. And then Larry and I worked on getting this into Isabel. And recently, like a random Chinese student, I think he was still a high school student at the time, just out of nowhere submitted this proof of the prime number theory with an explicit error bound, which you can see here. And it's just completely remarkable because, as you know, like learning interactive theorem proof is like a learning curve, like running headlong into a brick wall. And as a high school student with like no supporting system around that knows the system, that's just quite impressive. But this happens not very often, but it happens surprisingly often that like random people come out of nowhere with impressive developments like this. Yeah, Apéry's theorem. So that was like a quick project over Christmas for me. So there, I found this very neat proof by Bocas. Yeah, that zeta of 3 is irrational. Central limit theorem, that was also done ages ago, I think someone late 2000s. The law of large numbers, that's a bit more recent. Yeah, that every field has an algebraic closure. I think that was done by some interns of Larry's. And the Hermite-Lindemann-Weierstrass theorem, I'm going to show that on one of the next slides. So that's also something that I'm quite proud of because I always really liked this theorem as a student and I really wanted to have it in Isabel. And then a few years ago I actually did it. And so this is work that was done by a colleague of mine, a former colleague of mine, Fabian Imler. So he came up with he wrote a fast and fully verified numerical solver for ordinary differential equations. And he applied this to proving that the Lorentz attractor is chaotic, which is a fairly complicated proof that involves a lot of computer computations. And he basically tried to put these computer computations on a more solid ground. And if I recall correctly, he actually won some numerical solver competitions against unverified tools, actually, which is quite remarkable. And so lastly, I'm going to speak about this a tiny little bit on the next few slides as well. So I, together also with Larry and Wenda and Anthony Borge, formalized about 1.5 textbooks on analytic number theory. So not exactly all of them, like we omitted some of the exercises and some of the more technical things that we didn't actually need. Sometimes we found easier ways to do things as they were done in the book. But like roughly, I would say, yeah, 1.5 textbooks are there. And then, of course, there's lots and lots more stuff, a lot of probability theory, as I said, a lot of complex analysis, etc. So yeah, just generally speaking, there's a lot of maths there. Perhaps not as systematic as Lean's MathLib, but still there is a lot of stuff there that you can work with. And, oh yeah, this current work is not quite correct here. I forgot to update that. So as a part of my PhD thesis, one of the things I did, and this kind of started out as a unsanctioned procrastination project of mine, where I was supposed to do something else, but I really felt like working on something like this. So I started formalizing this book by Apostol, and then in the end, I think by now almost all of it has been formalized. Some of the more technical things might still be missing, but like all the highlights are definitely there. So the highlights include things like the prime number theorem, Dirichlet's theorem, and yeah, the definition of the Riemann zeta function on the entire complex plane. I think Isabel was the first system to have that as well. And recently I also finished the stuff about the partition function that's also at the end of the book. So that also ties into the additive combinatorics we saw earlier, I think. And then the follow-up work here is basically just taking the second book of the series and doing the same. And this is something that's been going on for a few years, and the problem is that all the people involved in it don't really have any time. But I've made a little bit of progress again in the past few months. So elliptic functions are now already in the archive of formal proofs, and also stuff like Jacobi theta functions, the pentagonal number theorem, that sort of thing, the dedicate eta function. I don't know if this means anything to you. Modular forms are, we had an ITP paper on that, so that also exists. It was of course published as an artifact for ITP, but it's not in the AFP yet because it still needs a bit of cleaning up. And the Rademacher's formula for the partition function, that's something I'm currently working on, and that's mostly finished. There's just a few little things to loose ends to tie up. So yeah, then that's about like the first half of the book, and the second half is I think it's not too difficult, but yeah, of course, you need to find the time next to all the teaching that you have to do. You know how it is. But yeah, so just as an example of what Isabel actually looks like in practice, so let's just look at an example proof that, like this. It basically shows that the norm of e to the z, where z is some, I think it's like something from a Banach space or something like that, that this is less than or equal 1 plus 2 times the norm of z. I've cheated a little bit here because we don't normally use this norm notation in Isabel. We just write norm of z. But this just makes it a bit more readable, so I just introduced this notation here. And Isabel allows you to, at any point, introduce notation like this and then delete it again later if you feel like it. So it's not like big cheating, because you can do this if you feel like it. And yeah, so basically the structure is that you make the structured proof. You can say, okay, I want to first prove this fact here, and then you might know this from Lean, like it also has these equation chains. So you can chain equations and inequalities together, say, okay, now I want that the left-hand side, the right-hand side of this thing is actually less than or equal this thing, and so on and so forth, until you finally show the actual goal, which is also up here. And then the only thing that's missing here is that each of these individual steps you have to justify, and this you do basically like you would also do it in Lean, by basically giving a tactic. And there's a bunch of different ways to do it. So this one here is just a single application of an explicit rule that you can find with the search function, for example. I'm pretty sure Sledgehammer can also find this if you don't feel like searching for it by hand. And then this basically is just, well, you just feed in a bunch of facts like the assumptions and some other fact from the library, and then you just call auto, and it can do it for you in this case. And this one is like a combination of the two that I'm quite fond of using. So you say, okay, I have this goal, and like the high level thing I want to do is I want to use the fact that the power function is decreasing if the argument, the first argument has a norm less than or equal 1. And then this, of course, has some side conditions that arise from it, and these side conditions you deal with by just feeding in the assumptions and calling auto, and then it just goes away. And then the final thing is basically just, I think it's just mostly getting rid of the power of one, that power of 1 to the first power is just norm of z, etc. And then that norm of z plus norm of z is 2 times norm of z, so this can be done just by simp. So that's generally the kind of structure that we use, and of course it's not always quite this neat and readable, but that's the basic idea. And yeah, and so the nice thing about this is that in principle you can read this even without running Isabel, because you can see what's going on, you can see all the intermediate steps, you can kind of follow the flow of the reasoning, and also when something breaks here, then you see exactly where it breaks and what you have to do to fix it. So that's also a big advantage. So then another example, so here I'm not going to show the proofs anymore, just to give you an idea of what's there in the library and what it looks like in Isabel. I mean, everyone who's familiar with Lean probably doesn't find this too surprising. So we have this binary relation, has integral, with, well, actually it's a ternary relation. It takes a function and a value and a set, and it just asserts that this function is integrable on that set, and the value of the integral is this thing here. So probably nothing too surprising. Then the prime number theorem, also not too surprising. So you just say, well, the cardinality of the set of primes less than or equal x is asymptotically equivalent to this thing, and the asymptotic equivalence is basically defined as, I think the quotient has to go to 1 or something like that, with some caveats about what happens if you divide by 0. So yeah. And then Hermite-Lindemann-Weierstrass is a little bit more complicated. So the informal statement is basically if you have a linear combination of exponentials where the coefficients are algebraic numbers and the exponents are algebraic numbers and the exponents are distinct, then this can only sum to 0 if all the coefficients are actually identically 0. And in Isabel, there's a number of different versions of this, but this is the one that I personally find the most elegant, is to formulate it as a list. So you assume that you have a list of pairs of complex numbers, and well, you assume that each of the pairs has algebraic numbers, and that it's the second components of the list are distinct, and you assume that the sum is equal to 0, and then yeah, you see that the first ones are actually all identically 0. So perhaps not too surprising. Yes, the question?
Backtick direct image?
Beg your pardon? Oh yeah, backtick is the image of a set under a function, yeah. Okay, so now let's move on to the Bernoulli numbers. So I assume that a lot of you probably will have a rough idea at least of what Bernoulli numbers are. Most of you will probably have a much better idea of what they are than I do. So you might have, well, I think you don't find it too surprising that the sum of the 0th power of I from I going from 0 to n is n plus 1. And if we replace the 0 by a 1, then we get this famous Gauss formula, or I also call, I think, the handshake lemma. It's also related to that. And you can, of course, increase this, and the realization is that whatever this fixed exponent is, you always get that this sum is a polynomial of degree, wait, I think it should be an n, not an m, of degree n plus 1. No, wait, what is this? I think this m should be a k. Yeah, you always get a polynomial of degree k plus 1. And this polynomial you can compute as, well, the difference of these two polynomials. And these polynomials, there you get this expression for these polynomials, where here in the coefficients you have these Bernoulli numbers popping up. And that's basically how the Bernoulli numbers were discovered, that people looked at this formula and tried to figure out a pattern here. And so these Bernoulli numbers are quite ubiquitous. So you can define them as, well, they're a sequence of rational numbers, and the easiest way to define them is by defining them as the sequence whose exponential generating function is z over e to the z minus 1. That's not exactly the definition Isabelle, so for historic reasons we define them in a more direct way, but then we prove this as a kind of derived lemma. And the nice thing about Isabelle is it doesn't have a notion of definitional equality, so any equality is just as good as any other equality. There's only one kind of equality. And that basically means that the definition doesn't really matter, so you can always, if you don't like the definition, you can always prove another equivalent definition later on, and that's kind of what we do. And yeah, so it's a sequence of numbers. You probably have seen this before. And it grows quite quickly, so if you plug in slightly bigger indices, then you see that, yeah, you have a fairly high growth. And yeah, what you can see is that the denominator actually fluctuates quite a bit. So for B60, for B60, it's this relatively big number, but for B110, it's already, again, a fairly small number. So the denominator fluctuates quite a bit, but the Bernoulli numbers themselves, as a rational number, have a fairly steady growth and can be approximated asymptotically quite well. And these things, they pop up everywhere in mathematics. So you've got Faulhaber's formula, which I already mentioned. You've got the Euler-Maclaurin summation formula, which is interesting when you want to connect the value of a sum to the value of the corresponding integral. They pop up in the Taylor series of various functions, like the tangent, cotangent, cosecant function. They have a connection to the Riemann-Zeta function because, for example, zeta of negative k is equal to this thing, and zeta at even integers is equal to this thing. And this in particular gives us this infamous Ramanujan sum that basically, if facetiously, the sum of all natural numbers is negative 1 over 12. And also to regular primes, and there's various combinatorial applications. So if you want to count the number of alternating permutations of a certain size, then you also get Bernoulli numbers in there. And yeah, all of these we actually have in Isabelle, except that for the regular primes, it's a bit cheating because we define regular primes in terms of Bernoulli numbers and not in terms of cyclotomic fields. The two are equivalent, but we don't really have a theory for cyclotomic fields so that yet. So we haven't done that. But everything else we have. And yeah, so some more properties. So this is fairly easy to show. Actually, all the odd index Bernoulli numbers are 0 except for the first one. And the sign of the even ones always alternates. So 2, 4, 4, 6 are all positive. And sorry, I messed up here. Yeah, I never ignore this, but yeah, the sign between the even ones always alternates from one to the next. So the sign is basically very easy to compute. And you can also estimate the order, the growth order, quite easily by just using the connection to the zeta function I showed before. The zeta function is very close to 1 for pretty much any inputs greater than 1. So the asymptotic growth is very easily deducible from this zeta function connection. And namely, both the Bernoulli numbers as a rational sequence and the numerators are of order roughly, well, their logarithm is roughly of order k log k. So basically the numerator has roughly k log k bits. That's already an interesting thing to know. And the denominator fluctuates quite a bit, but you can also estimate it reasonably well. It's very small compared to the numerator. And then the first more advanced thing that we're going to need is Voronoi congruence. So I don't expect you to like really understand this formula here, but the gist is that on the left-hand side we have the Bernoulli numbers, okay, times some factor, and on the right-hand side we have a sum from 1 to p, or p minus 1, over this thing. So this function, this congruence allows us to compute the Bernoulli number basically by computing this finite sum modulo p. So we can easily compute the Bernoulli number modulo p using this formula. There's a bunch of side conditions, of course, that I'm not mentioning here, but this is just the basic idea. And then another one that's very closely related is Kummer's congruence. And the purpose of this is that it basically allows us to, if we want to compute bk, we can basically reduce that to computing bk prime, where k prime is just k modulo p minus 1, and that just allows us to assume without loss of generality that our k is between 2 and p minus 3, which actually is a precondition of this one, if I recall correctly, or at least the modified version of this one that we use later on. So yeah, these two are the central ingredients in the algorithm that follows. So now for the actual computation, there's a bunch of different algorithms for computing Bernoulli numbers. They're actually quite hard to compute. So I've got the precise numbers in my ITP paper of the history of like how many of these were computed up to what point. But I think like up to the beginning of the 20th century, people only went up to like I think the 120th Bernoulli number or something. So you can, of course, you can just use the definition in terms of an exponential generating series. That gives you a recurrence to compute them. You can do that, but that's extremely inefficient. Then there's a bunch of cubic algorithms for computing it. We have, we have 2 of those in Isabel already. There's one based on something called the Akiyama-Tanigawa transform. And then there's another one based on computing tangent numbers via some recurrence. The second one of these also allows you to use entirely integer arithmetic and not rational arithmetic, which makes things quite a bit faster already. But for large inputs, this is still not competitive at all. So the modern algorithms to compute Bernoulli numbers are all quadratic or quasi-quadratic. So there's still like some logarithm in front of it. So one very neat thing to do is you can compute the power series, you can compute the formal power series of the tangent function by just computing the one for the sine function and the cosine function, and then dividing these two as, like truncating them and then dividing these polynomials. So that works quite well. Another thing you can do is, well, you can just approximate the zeta function to sufficient precision, and then you can basically read off the value of the Bernoulli number because you know the denominator, so you only you can easily compute like what is the precision that I need to be able to tell what the numerator is going to be. And this one in particular has the big advantage that the other ones don't have, which is you can compute a Bernoulli number without knowing all the previous Bernoulli numbers. So this, the other methods are quite good if you want to compute all of them at once, but if you only need one very big Bernoulli number, then this is the first one that was able to do that. And then the one that I'm going to talk today is a multi-modular algorithm that's fairly recent. and still the fastest practical one known. So there is one that is asymptotically faster, also by Harvey, but it hasn't ever been implemented, and Harvey isn't sure whether it actually is faster in practice because it's a bit more complicated. So the idea is that you just compute bk modulo p for many primes p independently, and then you just use the Chinese remainder theorem to read off the actual value of bk as a rational number. And so the high-level algorithm here is that the first thing we do is we use a prime sieve to compute enough primes. So what enough is a very delicate question, but let's just assume now that we have like an oracle that tells us how big the primes will have to be. Then there's something called the von Staudt-Clausen theorem, which tells us that the denominator is actually very easy to compute. Namely, it's just the product of all the primes such that p minus 1 divides k. So that's, once we have the prime sieve, we can just factor k, and then we have our answer. And then the next thing is that we approximate the numerator. So we saw before that we can do this just via the zeta function. We can get like an upper bound of how big is, like how many bits is this numerator roughly going to have. And then from that we can get a very precise estimate of how many primes will we need such that their product is guaranteed to be bigger than nk. And then the core of the whole thing is, well, computing nk modulo p for each of the prime numbers. And then, of course, we just use the Chinese remainder theorem to compute nk modulo the product of all of these primes. And then because we chose the primes to be so that their product is big enough, then we can just read off the result from that. Okay. So the only part here that's really performance critical is this computation of bk modulo p. And in particular, we can assume most of the primes have this property that 2 to the k is not equal to 1 modulo p. So I call these the nice primes, because there we can do something, we can do a lot of further optimizations. So I should of course mention that none of this was invented by me, right? All of this is from the paper of Harvey. I'm just formalizing this stuff. And basically this computation looks like this, that you have some outer for loop which has just a few iterations in most of the cases. Then you have an inner for loop which is chosen such that you have a very large number of iterations, so many millions, perhaps even billions of iterations. And then in the loop body, what you do is you compute 64 bits of the binary expansion of 1 over p. And then you split this up into 8-bit blocks, and for each of these you add some value that you compute from that to some table that you maintain. And afterwards, after this entire inner and outer for loop has run, you have to consolidate this into one final result. So basically it's just a kind of a weighted sum of all the table entries. And so yeah, the important thing is that this inner loop has to be extremely fast. So the whole thing is optimized so that in the inner loop you're barely doing anything. And yeah, and the size of the blocks also, so why is it 64 bits? Why is it 8-bit blocks? So all of this has been optimized in such a way that on a modern CPU, everything you're doing fits comfortably in the level 1 data cache, so you will never have to do any memory accesses. So this is very important. And this only yields a constant factor speed up compared to just computing the sum more naive way. But the constant factor in this case, so Harvey claims it's about 200, so it's quite significant. Okay, and so how did we actually do this? So there's this thing called the Isabelle refinement framework, and what it allows you to do is you can have a abstract algorithm where you do computations with natural numbers, with integers, etc., and you just write, oh, let p be the smallest prime factor of n, or let k be the order of n in the ring z over pz, and you basically don't talk about how you compute these things. You just like use them in a abstract mathematical way, and then you refine this down to more concrete implementations where you use for and while loops, where you say, okay, I have my prime sieve is a list, and I plug in the values one after another with a for loop, or the order I compute from the factor. First I compute a factorization with the prime sieve, and then from this factorization I read off the order, etc. So you just concretize the things, but you're still doing all the computations on natural numbers and integers. And then the next step is that you refine this down further, and now you say, okay, I want to implement natural numbers and integers with 32-bit integers, 64-bit integers, etc. And of course, you will now need additional assumptions, because if your numbers get very big, then you might have overflows, so you have to prove that there is no overflow, or if there is an overflow, then it's fine, it doesn't change the result, etc. And so this has been already used for some very big examples. So there's the ISA-SAT, which is a fully verified SAT solver, which is not quite competitive with state-of-the-art SAT solvers, but it's pretty good. So it does compete in the same categories as these at competitions, and it does reasonably well. And also Lammich verified a bunch of sorting algorithms that he refined down all the way to LLVM. So I don't know if you know what LLVM is. It's basically like it's a bit like a more abstract version of an assembly language that is machine independent, but it's very low level. So, and he did these verified sorting algorithms that refined all the way down to LLVM level, that when you run them, they are just as fast as the ones from the C++ standard library, but they're completely verified. And so basically that's what we also did here. So just as one example, so on the abstract level, the smallest divisor function is defined as, well, if you give it a natural number less than 2 or a prime number, then it just gives you 0. And otherwise, it gives you the least prime factor it gives you the least non-trivial factor of that number. So it will obviously also be a prime factor then. And this basically just allows you to very easily check, first of all, is my number prime or not? And if it isn't prime, it allows you to very easily factor the number just by like repeatedly calling this function, dividing out the smallest divisor, etc. And the idea is that we want to build a cache that just tells us for every number up to a certain bound what is the smallest divisor. And so we just define this factor cache info function, which is, it takes a natural number and it returns a function from natural number to natural number, which implements exactly the smallest divisor thing here in the non-deterministic result monad. So this is just some monadic thing that we use to specify these algorithms. So here on the right-hand side, you would have like some while loop that computes the factor cache. And then we prove that this implementation of the factor cache satisfies the specification that for all k less than the upper bound n, it is the case that a of k is actually the smallest divisor of k. And this proof is, of course, that you have to do some work there. You have to give like loop invariants, etc. So this is basically program verification, but there's tooling to help you with that. And then there's further refinement where you say, okay, instead of having a function from natural number to natural number, we now just want to actually have a list of natural numbers. So this is a fairly simple refinement that's mostly automatic, I think. And there what you prove is basically, it's a bit more difficult to read, but basically you just show that the new implementation refines the old implementation with respect to some refinement relation that you specify here, and the refinement relation basically just says that, well, the entries in this list here are exactly the ones returned by this function here. And then the next refinement is that you replace lists with arrays and you replace natural numbers with words. So words in Isabelle are just basically integers, but only up to 2 to the power of some width, some bit width, -1. And this is also mostly automatic, I think. And also what's already happening here is there's quite some magic going on in the back, because here you're also replacing a functional implementation with an imperative one with destructive updates. And all of this is just managed for you behind the scenes. So the thing basically just like sets up everything such that you can have destructive array updates, and it just works. Yeah, and then in the end you get this I don't know how easy this is to read for you, but the theorem that you get here is that, again, this concrete implementation in the imperative world refines this more abstract version on lists with regards to this refinement relation, which says, okay, the input is a natural number, and the output is a pair consisting of an array and a natural number. I forgot what this natural number is for, but yeah, so this. And the array, of course, is refinement of the list that we had before. And this is what the final correctness theorem looks like. It's, of course, this is completely unreadable, but that's normal because this is separation logic. So separation logic is something that you need when you want to reason about like memory, heap memory, and pointers, and it just becomes very complicated. But the relevant part is this one. So this one says that we have this flag OK, so this is part of the output. And if the OK flag is non-zero, then that means that actually the algorithm succeeded. And then if it succeeded, then the denominator that we get is actually the denominator of the Bernoulli number of k, and the numerator is exactly this thing. And then the second thing is that we have a guarantee that whenever k is at most this number here, then the OK flag will actually be true. So the algorithm will succeed at least for all numbers k up to this bound here. So that's roughly 10 to the 8, or I think roughly 2 to the 30. And for anything bigger than that, the problem is just that we might run into overflows, and it's very hard to predict when exactly we will run into overflows. So we basically have this more dynamic thing where we have this OK flag that tracks if we run into an overflow or not. Okay, so what were the challenges? Well, first of all, there's just a lot of things that go into this. So you have to prove a prime CIF algorithm correct. You have to factor integers. All of that is done. Then you have to do group theoretic computations. You have to find generators of this ring Z over PZ. You have to compute the order of an element in that ring. It doesn't have to be super efficient, and as far as I know, there aren't really any efficient algorithms known for this. The Harvey's implementation just brute forces it. We are a little bit smarter, so we use the prime CIF that we already have to just factor the number and then read off these results from the number. But especially finding generators, you basically have to brute force it anyway. So all of that is done. Then we have to do efficient computations modulo P, and we're doing a lot of these. So there we're using something called the Montgomery form, which is just something that allows you to do computations in the ring Z over PZ in a more efficient way. So doing multiplications basically without then having to do a division to reduce it back to normal form. That's also done. Then there's a bunch of floating point computations in Harvey's algorithm, and floating point numbers are always kind of problematic. So there we just replace them with equivalent fixed point computations. And then there's this thing about computing the binary fraction expansion of 1 over p. And then another big thing is that at the very end, when you do the Chinese remainder theorem, so up until the very end of the algorithm, you don't need big integers. You can do everything with 32 bits or sometimes 64 bits. But then in the very end, I mean, the final result is a very big number, so you're going to have to compute with very big numbers. So there, basically, the question was, what do we do about that? Do we build a library of arbitrary precision integers? And we ultimately decided against it for now, because this is a lot of work and it's really out of scope for this work. So Peter Lammich just found a way to integrate the GNU multi-precision library, which does arbitrary precision integers, into this as a trusted component. So yeah, we have some lemmas in Isabelle that basically just say we assume that GMP does these computations like multiplication and division in a correct way. And well, possible future work would be replacing this with an actual fully verified implementation of arbitrary precision integers. Other systems already have this. I don't know how efficient they are, but I also suspect that it's not like a performance critical part of the algorithm. So as long as we have like a decently fast multiplication and division, it should be okay. And yeah, then there's the fast Chinese remaindering in the end. So if you do Chinese remaindering the naive way, then this is extremely inefficient. So you have to come up with something quicker. So there we use something called, I think, remainder trees. It's called. And yeah, this is, remainder trees, exactly. And yeah, so this was also implemented. And yeah, you need a lot of mathematical background as well. So of course you need the definition of Bernoulli numbers and some basic properties. So this was already done a few years ago. Then you need the bounds for the Bernoulli numbers. That was easy because we have the zeta function. Then you need these comma and Voronoi congruences and Harvey streaks to them. So this I did fairly easily. There was a like the original proof that I found uses p-adic integration, and I don't know what that is. So someone on Math Exchange was kind enough to point out an elementary proof to me in a book, so I just formalized that instead, and that went without any problems. Then another slight complication was that we had the prime number theorem, of course, which tells us the asymptotic distribution of primes, but we also needed something more concrete, so we really needed the concrete bounds for the Chebyshev theta function, which basically tells us what the growth of, if I take the product of the first n prime numbers, or alternatively of all the prime numbers less than or equal n, how big is that roughly going to be? And so the precise bound that I formalized is this one, that basically says, yeah, that the sum of the logarithms of the prime numbers less than or equal x is greater or equal to 0.82x. And the prime number theorem basically says that in the limit for x going to infinity, this thing is going to be roughly x. But you can prove for a sufficiently big concrete x, you can prove that this okay-ish lower bound, and that's all we needed really. So this is needed for our very first a priori estimate. How many primes do we have to sieve in the first place in order to be sure that we have enough of them? So that's also done. And here's just an overview of how big everything is. So we are at big proof, and I would say this is a big proof. So the Voronine comma congruences are about 2,300 lines, and then the prime bounds I just mentioned are another roughly 2,000 lines. Then these are the more concrete implementation things. So we needed about 1,000 lines to just make a verified fixed point implementation of the binary logarithm of a natural number. So this again we need for the estimate of how many primes we need. Binary fraction expansion, computing the binary fraction expansion of the number 1 over p, that's another 900 lines, Montgomery multiplication, etc., etc. So I'm just going to skip over this a bit more quickly. And so these numbers are fairly big because this is no longer just like abstract mathematics, but this already has like concrete algorithms in there. And generally speaking, computer science is always much more verbose than mathematics. So computer science developments are sometimes, I think we recently had one that was like 100,000 lines. Whenever you have like algorithms, then stuff tends to be less dense and more verbose, I would say, in formal proofs. And then there were some additions to the separation logic packaged by Peter Lammich, so stuff that was missing from that. So we identified quite a lot of parts where this framework was not general enough and where you will have to do some improvements in the future. And then these trusted GMP bindings also took quite a bit of lines of code. And then the abstract algorithm, so basically just the mathematically abstract formulation of the algorithm is about 1,500 lines of code. And then the concrete algorithm, so refining everything down to LLVM using all of these components, that's another 8,500 lines. So in the end, we have a little bit more than 30,000 lines of code, which is not too surprising for something this like concrete and low level. Yeah, so just one quick look at some concrete optimization, why this all gets a bit messy. So one thing we have to do, as I mentioned several times, is compute the binary fraction expansion of 1 over p in these 64-bit chunks. And so the high-level algorithm, how you might want to do this is, well, you just left shift. So bitbuff just holds the initially this is just 1, and this basically just holds the modulus at the current the remainder at the current point. So you just left shift this by 64 bits, and then you divide over p, and then that's the next 64 bits in your expansion, and then the new remainder just becomes the remainder of the same operation. So this works. The problem is it's expensive. So what we do instead is we pre-compute once at the beginning of the program. We compute a 128-bit fixed point approximation of 1 over p. So basically just 2 to the 128 divided by p. And then you can replace division with multiplication, and you can just compute the new remainder. I know you can compute the. Okay, you can compute the quotient as well, this 1 over p approximation times the current remainder, and then left shift the result by 64 bits. And the new remainder turns out to be just negative p times this thing. And the problem here is that there is actually a small chance that the computation is off by 1, so that the quotient is actually too big or too small. I forgot which one it is. And in that case, you have to introduce an extra check and like reduce the quotient by 1 again and adjust the remainder in the same way, but it still ends up being much faster than the naive computation above. And so, of course, you have to prove that this is correct, and it's actually quite subtle. So there's a lot of side conditions here, like how many bits, how precise does your this inf p actually have to be? So it's quite challenging to figure out the side conditions there. So in the C code, so this is not part of the Isabelle code, but that's basically the C code that I wrote in the beginning, just as a prototype, and that's roughly the pattern we follow for the formalization. Looks roughly like this. And then, yeah, in the end, you have like this check where you say, well, is it the case that this x, so the remainder, is now greater or equal than p, which should not be the case? And if this is the case, then, well, we increase the quotient by 1 and we subtract p from the remainder, and then everything is okay again. And it turns out that this thing here, it's so unlikely. I think it's like something like 2 to the power of negative 32, that because modern CPUs have branch prediction, that basically the branch predictor will realize that this basically almost never runs, so it costs you, effectively costs you nothing in practice. Okay, now of course, proving such very low-level stuff correct, first of all requires you to figure out, so why does this even work in the first place, which is not that obvious. Then you have to figure out, well, what preconditions do I need? How precise does my approximation have to be, etc.? Does overflow happen? If it happens, is it a problem? Or can I argue that it doesn't actually matter? And this can be very painful, but the advantage is that I would say, like with pen and paper, or just with intuition, it's very difficult to figure out exactly like what are the edge cases. Where does this not work any longer? And with a theorem prover, you can very precisely figure out what are the preconditions. So how far can I push this, and what are the consequences? So, for example, you saw this earlier in the correctness result. We said that the algorithm is guaranteed to give you the right result up to this number, 10 to the 8 or something like that. I think this is very difficult to figure out this exact number without a theorem prover. So you really just reduce to kind of making like an estimate with your intuition, and then making some tests, and then hoping that you didn't miss anything. So yeah, it's definitely nice to have this formalized. So yeah, evaluation. So this is just a plot of the relative performance of our verified algorithm against Harvey's unverified algorithm on various hardware. So the interesting thing is that, so the single core performance here, you can see it follows a quite predictable pattern, except that there's like these few jumps, these little jumps in here. I have no idea where these come from, so this requires some micro benchmarking that is very much beyond me. And then on like the big cluster machine with 64 cores, it becomes much more noisy. But the interesting thing is that there we're actually quite a bit faster than Harvey's algorithm for a long span. I have no idea why, because both of them are multi-threaded in a very obvious way. So yeah, it's just benchmarking these things is just a nightmare. But in any case, I would argue that especially for large inputs, we have comparable performance to the unverified algorithm. So we're like around 30% slower on big inputs in the worst case even. So it's kind of okay, I think. So in here you can see the single core performance in a bit more detail. So yeah, you can see it's fairly predictable, and it's not too far off from the original one. So as a conclusion, yeah, so I think we can say that we verified a fairly complex and challenging mathematical algorithm. I should mention that I'm not sure if this is actually useful for anything. I have like an unexplainable obsession with Bernoulli numbers, and I just thought this was a very neat algorithm, so that's why I wanted to formalize it. And I think it led to a lot of nice reusable components, and it showed us some problems with the existing infrastructure. So in that case, it was definitely useful. I think there are some mathematical conjectures which actually require you to compute Bernoulli numbers, even sometimes also Bernoulli numbers just modulo a prime number. So it's very nice to have this as a verified reference implementation. You can also use this to basically certify or like at least sanity check computations of Bernoulli numbers done by unverified code, because what you can do is you can just pick a random large prime number and check whether the Bernoulli number modulo k matches the number that the software produces modulo k, modulo p. And if you do this for a few prime numbers and it always matches up, then the probability that you have that it's wrong is very low. Yeah, so as I said, it resulted in various additions to this existing framework and showed some weak points. And yeah, the performance is not quite as good as the unverified code, but I think that's not so much because of like some insurmountable obstacles in our verification. It's more like I don't know enough assembly to figure out what's going on there. And if we could figure out where the bottleneck is exactly, I think it shouldn't be very hard to change our verification to make it work. Yeah. Okay, and also yeah, we're much faster than Mathematica already, because Mathematica I think is still using the old algorithm based on the zeta function, which is decent, but just not as fast as Harvey's. Okay, that was it. Thanks for the attention.
So we have 3 minutes and 22 seconds for questions, which gives us, I would think, well, 2 or 3 questions at least. Back right-hand corner. Hello.
You mentioned that you added GMP as sort of a trusted external tool. Does Isabel have a way of tracking that you added these as like axioms or like terminal extensions or whatever you want to call them?
Honestly, I didn't look at how exactly Peter did it, so I'm really not sure how, what's going on there. So I mean, I think like at the end of the day, the stage where there's always some verification gap, right? So you have some LLVM syntax tree in Isabel, and you have the theorem that basically if you evaluate the syntax tree with the semantics of LLVM in Isabel, then you get the right result. But then of course there's the verification gap. First of all, is this semantics the actual LLVM semantics? Is the LLVM compiler correct? Are the primitive functions in Isabel LLVM, do they correspond to the actual primitive LLVM functions that are executed? And I think this is basically one of these cases as well, where Peter basically just assumed, okay, there are like these functions of GMP, and I just print them in this particular way, and then I assume that it works out correctly. So I think it's really just part of this assumption that the printing of the LLVM syntax tree is done the right way. So yeah, I don't think there's an easy way to really track that now.
More questions? Paul?
Yeah, could you explain what's happening with the parallelism? Is it the compiler of the LLVM that's inserting parallelism, or are you?
No, we're explicitly doing that. So so Isabel LLVM has some parallelism primitives, and these are then in the end mapped to, oh God, I actually have no idea how this works how this works exactly, but, oh yeah, right now I remember. So this is again one of these code printing issues. So we're using a library called TBB, Intel Thread Building Blocks, and this just has a function that takes, I think like some continuations and then basically runs them in parallel. So we're assuming that this thing also does the right thing. Yeah.
Any more questions? Hello.
Oh no, I was about to come.
Oh, you're about to come. Any more questions? There's a question. Yeah.
Yeah, just a remark. You said, oh, I'm not sure how this is useful. I think a lot of the it's an amazing talk. So thank you very much.
Thanks you.
How this is used in practice, and we're using this all of us every day, is in crypto. So a lot of the building blocks you're using here also used in the main crypto libraries, and we're running them in the Linux kernel, in TLS, in the Python libraries.
Well, presumably not Bernoulli numbers, but like prime sieves, you mean, and like generators,
and the Montgomery algorithms and so on.
Yeah, I mean, I suspect that verified implementations of this stuff exists elsewhere. I mean, they have verified cryptography at I think at Amazon Web Services and at Apple, but they're of course a bit secretive about these. But yeah, I suspect that this is not particularly novel or anything, and it's not very difficult either. But it's just that there's a lot of things that you need, and that of course makes it a bit challenging.
Last one.
Okay. Yeah, I was just wondering, because a lot of the stuff here is analytic number theory, and you mentioned that you had to define regular primes in an ad hoc way. And you mentioned that it's an issue with cyclotomic fields. Is it just generally that algebraic number theory packages are lagging behind in terms of like defining a class group? For example?
Well, there are no algebraic number theory packages in Isabel, and the reason is not necessarily that it would be hard. I think it's really just that there hasn't been an Isabel user so far who has cared about natural algebraic number theory, I think. So there is a bit of a difference, I think, in the audience, right? So Isabel is very much a system that was developed by computer scientists who, of course, knew a little bit of maths because you learn some maths as a computer scientist, right? but they like when they formalize stuff that they either needed for something concrete or that they just found was neat, and that was of course typically like the kind of mathematics that you might know as a computer scientist. So typically more elementary stuff. And whereas Lean is more a system of mathematicians who know all this like crazy advanced maths, and they want to formalize the crazy advanced maths that they know. And so that explains just the different focus of the library, I think. And Isabel is only starting to get like people trying to formalize like more advanced graduate level mathematics. Well, that's not quite true, but like the focus is beginning to shift a little bit more. So I've done a bit of analytic number theory because I kind of like slipped into that. And I think the same hasn't happened for algebraic number theory. So I have like some vague plans of doing something with number fields, but I don't know anything about number fields, so that makes it a bit more challenging. And so generally, I think Isabel has some problems with algebra. So doing algebra in Isabel is not as nice as it could be. The libraries there could be improved quite a bit. I haven't done much algebra myself in Isabel, so but I think number fields actually should be kind of doable. And you said that I had to define regular primes this way. I didn't actually have to do it because I didn't need them for anything. It was more like, so one of the nice consequences of Kummer's congruence or Voroniz's, I forgot which one it was, is that there are infinitely many, was it regular or irregular primes? Irregular, yeah. There's infinitely many irregular primes, so that I just wanted to have this as a kind of nice side result, so that's why I defined it that way.
Okay, well, on which note, unless Larry wishes to... No? Thank you very much indeed.
Thank you.